Okay, a little bit of delay. The next speaker is Silvia Berra from the University of Genoa, and she will talk about a fast and accurate method for colorectal cancer cell steady-state computation. So, Berra, the stage is yours.
Thank you, Alessandro. So yes, I am Silvia Berra from University of Genova, and I will talk you about a method for computing the equilibrium points of chemical reaction networks with a particular focus on colorectal cells. So my work is inserted in the context of LISCOMP Lab, that is a laboratory, a computational laboratory, that is part of the MIDA group inside the math department of the University of Genova. And so I collaborate also with San Martino Hospital, because also physically the LISCOMP Lab is inserted inside the hospital. And I also collaborate with a pharma company that is Roche. And now I am working on this work that I'm going to talk to you about, and I'm going to submit a paper, hopefully in a few days. And yes, the work is joined together with Sara Sommariva, Alessandro Latorraca, and Federico Benvenuto from University of Genova and Roche company. So let's see a brief outline of the talk. I will start by describing the biological background that's behind the work I am doing. Then I will go on by passing from the biological world to the mathematical one. Then we will see the main part of my work, that is the PNG algorithm. This is the name me and my collaborators have given to this algorithm that serves for computing the equilibria of these chemical reaction networks. And then in the end we will see some results and some ideas for future works and things like that. Okay, so starting from the biological background, let's consider working with a cell of the human body. Okay, these cells receives signals from the outside and translates them into intracellular responses. And this is done by very big networks, of chemical reactions. But these networks can have some issues, some problems when there are alterations of them that generally are due to mutations. And so they can cause diseases like, for example, cancer. What we want to do is understanding which are the drugs that we should use when there is such a disease, so that they can act on specific nodes of the network and restore its original behavior. Speaking of mutations, we can have two different types of mutation that abolish or increase the function of a given protein. But what is important is the following. So if we work with a cell in the physiological status, as you can see here in the figure, we have some initial, in a specific phase of life of the cell, we have some initial concentrations of proteins inside the cells. Then there is the action of the chemical reaction network. And after this action, we find equilibrium concentrations. So this cell, inside the cell, these concentrations vary in time till they reach a situation of equilibrium. The same happens when we have a mutated cell, but what is the difference? The difference is that with some mutations, we can have different initial concentrations, and we can have a different chemical reaction network. And this obviously leads to different equilibrium concentrations. So what we want to do is computing these concentrations and doing a comparison to understand which drugs the patient should take for restoring the healthy status of the cell. Okay. The chemical reaction network my work is focused on the most is the following, that is the one associated with the G1S phase of life of colorectal cells. This is just to give you an idea, because actually here you can see so many nodes, but the real nodes of these networks are 419, that are the proteins involved. And then we have also many chemical reactions, that are 850. And okay, so this is the network we want to find the equilibrium of. But how can we pass from the biological world to the mathematical one? the network we have just seen can be described mathematically in this way, so through a system of ordinary differential equations. Here, what we want to know is the values of the function x of t that represents how protein concentrations vary in time. So x represents the protein concentrations, x naught is the vector of values of initial concentration, so at the beginning of the phase of life of the cell we are considering. And then we have S, that is a matrix called the stoichiometric matrix, V, the vector of reaction fluxes, and K, that contains some other parameters of the network that are the rate constants. Okay, so if we look at this problem and we think, okay, we want to compute the equilibrium of this system, generally what we could do is using a dynamic approach, so trying to compute the function x of t at different times, and then going to see what happens when we go on with the time, okay? And so we could try to find the equilibrium this way, but the point is that this method, we will see later, is not so fast and too much accurate, and this is the reason why I am going to introduce another different method for this purpose. Okay, we have to consider that the function x of t must not only satisfy the system we have just seen, but also some laws that are called conservation laws, and that are made like that. So we have the vector gamma. It's just yes, a combination of the linear combination of the components of the vector x that must be equal to a specific constant at all times of yes, at all times. And so we can create this way a matrix n that has as columns these vectors of coefficients, and say that the conservation laws that the vector must satisfy is this one. Okay. So the problem we have found is the following. We want to find the function x of, the value of the function x of t at equilibrium, and we want this value also to satisfy these conservation laws. So if we look at the problem like this, we can think, okay, since we want to find an equilibrium, probably we don't need to know what happens at these concentrations at all times, but we just can get directly to the point and trying to understand what happens at equilibrium. When we have an equilibrium, generally we have that the derivative of the function, very trivially, must be equal to 0. And this is exactly what we do. So we consider that problem that before was a dynamic problem, and we look at it just as a root finding problem. So we want to find the vector x such that this object is equal to 0, and we can find it here, and then the conservation laws must hold. The only problem is that now we have a system that is not squared, so it could be not so easy to compute the solutions, and this is why we add an assumption that luckily is effectively true in our case. So when we work on colorectal cancer cells, it holds, so it is very good for us. And so we assume the matrix N to be, as we say, weakly elemented. That means that the matrix can be divided in these two submatrices, where the first one is the identity matrix. So we can divide the vectors, the columns of this matrix, and the same way we can divide also the vector x and the matrix S, just by reordering some components of the vector and of the matrix. And so now we can write our problem this way, where, if you remember, the only difference from the previous slide is that here we have this S2 and not the S we had before. And this is good for us because now we have a square problem, and what's more, we have proven that these two systems are equal. So they have exactly the same solutions. So we can consider now this problem here. Which is the approach we choose to use? First of all, we all know that when we are trying to solve a root finding problem, what we can do is applying the Newton method. And so this is what we are going to do, but we are going also to combine it with a different method, that is the gradient descent one. Why? Just because if I am looking for zeros of the function f, it means that I'm looking for minima of the norm of the function f. And so I can look at the problem from both points of view. On the one side, I look at it as a root finding problem, and on the other one, I look at it as an optimization, a minimization problem. In both situations, I do backtracking thanks to the Armijo rule, so I don't move along the whole direction, but sometimes I decide to move less. And when I apply the gradient descent method, I also impose another condition on the choice of the step length, but we will see it later. Okay. We have also to remember that what we are looking for is concentrations of proteins. So obviously we can't have negative values for these for the components of the solution vector. And this is why we should somehow project on the positive convex cone for having all positive or zero values. So naturally we could use the orthogonal projector for doing that, but what we have chosen to do is to apply a different operator. We will see why, and this operator is very, very simple. It is done like that, it behaves like that. If we start from, as you can see in the figure, from a value x, a reconstruction at the iteration k, then we try to move along a certain direction that can be decided through the gradient descent method or the Newton one. Then we, if we fall out of the box on a certain component, we decide not to update that component. So our next iteration will be this one. So we update it only on the first component and not only on the second one. And as regards the condition I was talking you about before, so the condition on the gradient that must be satisfied for choosing the step length at each iteration when we apply only the gradient descent method, it is the following. It is not so easy, I think, to understand at the first sight, but if we look at the image, we consider starting from a point xk, we move along the gradient descent direction. If here there is a minimum, it is probably we will go to this minimum, and then applying the projector, we would go back to this point. But what do we ask the step length to satisfy? We want this red part to be bigger than the green one, where the red part indicates the quantity we can move on if we choose that alpha. So we can move along for this segment if we choose this alpha, that here is equal to 1, but we don't move along this segment here. But we want the red part to be bigger than the green one, and this is why in this case we would choose a smaller alpha to stay inside the box on more components than the ones we had before. And so in this case we move on both the directions, so I have colored them both in red. And so now the sum of the red parts is bigger than the sum of the green ones. Okay, in this case we have no green components because we have only two. Okay, we are in R2, but okay. Why have we chosen to add this condition? Because this condition allows us to give a result also from a theoretical viewpoint. Indeed, if we have a sequence of reconstructions and this sequence has a limit point, then this limit point is a stationary point for this function here, so for the norm of f. And so this way we are pretty confident that we are going towards a good point, the point we were looking for. From a more applied viewpoint, okay, let's see now why we have chosen to use the non-projector and not the orthogonal projector. We decide to do that because, for example, let's consider this situation. We have a cell with initial concentrations at the beginning of her specific phase of life. So we have some values of x naught. Then we construct all the reconstructions of these of the solutions, one iteration after the other one. So you can see here we have 500 iterations. When we apply the orthogonal projector, you can see the results in green. The percentage of components that are equal to 0 on the reconstruction is nearly the 40% of the components. So it is a very big number. Whereas if we consider the non-projector, and we can see the result in red, the first thing we notice is that in this specific case, the method has led to convergence in about 90 iterations, whereas in the other situation, after 500 iterations, we don't have the convergence of the method. And at the same time, we see that we don't have so many null components of the reconstruction, but I can say we have no one component that is equal to 0. And this is good because when we have too many zeros, the condition number of the Jacobian matrix of the function becomes too high, and this leads to many instability issues, so numerical problems that we wanted to avoid, because those problems meant also more time to obtain results. And before I was talking also about the dynamic approach, the possibility of applying a more dynamic approach for solving the problem. Let's see the results of a comparison for what concerns both precision and elapsed time. For what concerns accuracy, you can see in the first graph here, we have considered different mutations of the cell in her physiological status, and then different mutations. In all cases, we have in blue the results of the PNG method, so our method, and in red the results of the dynamics. I don't know if it can be seen so well, but the red results are all here at the top of the graph, whereas the PNG results are here. And this means that there is a very big result in the norm of the function f that we have computed in the equilibrium point we have found. So actually we wanted the norm of f to be equal to 0, and so in our case we have definitely better results. There is a difference of an order of magnitude of about 12 or 13. Okay, and for the computational time we can see a similar situation because we have always better results in the PNG case, even though here the dynamic is more sensitive to system variations, and so we have more differences. But in the end, we can say that also in this case, the PNG method outperforms the dynamic one. Okay, so what we have done is defining a new method for solving root finding problems. Above all, if we work with the box constraint, because that's the only possibility where we can apply the non-projector till now, if we want to modify it some way. And then we have seen that so the non-projector can help us to have positive solutions to avoiding numerical problems. Our method also outperforms the dynamic method, and what's more, we have been also able to prove a result of convergence of the method. As regards future work, it is not so easy to know how a chemical reaction network works, how it is done. For example, of the human body in literature, I think there is only this network that is known, and some characteristics of other networks, but not so many. So our goal would be the one of creating other chemical reaction networks using natural language processing, and having a fast and accurate method for computing equilibria starting from the knowledge of the chemical reaction network would be a good point to start for obtaining also this result. So thank you very much for your attention, and if you have questions, I hope I will be able to answer.
For the nice talk. There are some questions from the audience.
I have a small question about the step length. You said you're using a Mijo type of tracking. I was wondering if you have considered also adaptive strategy that allows the step size to increase locally during the iteration. If locally the Lipschitz constant, for example, is good.
Okay. No, I didn't
maybe
consider that.
It goes against the other condition. I don't know.
No, I must be honest, I haven't thought about that. Probably it could be an idea, because sometimes it would be better to have also a better condition for choosing this step length, but I haven't considered it. But no, okay, I will ask you. Okay.
questions? If not, add one. So the fact that you don't project to the border, to the boundary of your domain, it just means that you're assuming that the minimum of the function is not on the boundary, but you prefer to search it inside the domain, right?
Yes, actually it is not so easy to obtain zeros, to obtain components with values equal to 0. But we have considered that we can also arrive to the boundary by moving on the inside of the box.
So the step length there.
Yes, exactly. Because also the condition I have added helps us to choose a smaller step length that can help us to arrive to the boundaries of the set. Probably you don't reach exactly the 0, but you are really, really close. So it's just a matter of, I don't know, numerical error. But we have seen the pros and cons and decided that it is better in this case.
Okay, so thank you, Silvia, again.